right, good afternoon. Welcome back to Chemistry 401. Please have a seat. We'll worry about these later. So the 2 pages that I passed out, those are actually 2 pages that will replace your lecture notes at the end of Chapter 18. For those of you playing along at home, you realize that we're finishing up Chapter 17 today and starting Chapter 18. As I was writing up and looking at my notes for Chapter 18, I realized there was a better way to finish the thermodynamics story for Chapter 18. So, in your Hitchhiker's Guide, you'll see there's already a page 188 and a page 190 in there. I think they're 2-sided, so replace it with those. Happy to talk about that. Make sure you have the right thing. You'll see my lecture notes go. In a couple lectures, they'll just continue right on to that part. Marissa, question?
Unrelated, but for lab next week, will we do the lab from this Monday or is it going on?
Great question. What are we doing next week in lab? This week's lab on equilibrium constants. So if you prepped for it, then you're prepped for it. If you're not, well, good news, you will be prepped for it by next week. So go ahead and have a seat, Angel. Please don't pick those up. Thank you. So I will remind you, and it's not a big deal, but once I start lecturing, if you needed it, I would let you get it, but you don't. Just make sure you get it, or if you need it for today's lecture. Anyway, so it'll be there. Pick it up afterwards if you have any questions about it. Question, Esperanza?
In reference to our lab, which is today, what do we set up for?
You will be doing this week's lab next week.
Okay, so
Their lab was canceled this week.
nothing got
Surprise. Yes, nothing got changed. Nothing else got changed. Jamie?
The green homework for chapter 17, 2 weeks from
Good question. So when is the chapter 17 homework due? So here's what we need to do before the next exam, which is 3 weeks from today. We need to do chapter 17 homework and we need to do chapter 18 homework. So you should pace yourself accordingly. So if you take 2 weeks to do chapter 17, you have 1 week to do chapter 18 and study for the exam.
Are they due on the exam day then?
However, chapter 17 will be due 2 weeks from today, and chapter 18 will be due at the next exam. Okay? So that way, but anyway, pace yourself. By next Wednesday, I will have chapter 18 homework for you, and soon thereafter, a practice exam 2 as well. A couple other points of information. I will be attending the American Chemical Society meeting the week of your next exam. That means I will not be there that Monday. I will not be there that Wednesday. You will have subs for the entire week, including a sub to proctor your exam. I don't imagine this is going to be a problem, but I do need you to bring an ID so that when you turn in your second exam, we can make sure, since I'm not here, that you are who you say you are. And anyway, it's probably not a problem, but if you know how I run my classes just in case something could go wrong to make sure that it won't. Vivian, question? No, Marissa, question?
Do you know who the sub is going to be, and then also so you're not going to be good at answer questions?
So, do I know who the sub is going to be? Until I have a very good idea, but until I confirm, I will not say. He is an established Chem 401 instructor, that I can't say. And then the other question, since I'm not going to be here the week of the exam, you will tough it out. And so you know this ahead of time, so if you want to ask me any questions, your last day to see me is the previous Wednesday, because I leave town that Thursday morning. Well, I hold additional office hours that week. Honestly, probably not. But trust the process, right? I know. Exam 2, nobody wants to have to trust the process for. They want the process to be spelled out and done. However, so I would, even in my absence, I hope to take care of you, whatever that means. So No, practically speaking, and I get it. So Chem 400, we talked about this a lot, about what to expect on the exam. Chem 401, just as scary, if not scarier than Chem 400. And so I will talk to you about what will be on the exam, the expectations of the exam as we get closer to the exam, all the way up until I leave. And then that exam, I will run through, it will be, well, like, you will not need me to answer any questions about it, because it will be that good. And anyway, as we get closer, as I actually make it up, we'll talk more about it. But anyway, so if you can, trust in the process. I will take care of you. I will make sure that even in my absence, things go okay to good. So, and if they, and in the very, very tiny chance that they don't, we'll talk about it when I get back, and we'll fix it all then. So, because my goal, I mean, what are my goals for teaching this class? That you learn a lot of chemistry, and I see lots of people learning a lot of chemistry, and we will make sure the exam grades and your final grades reflect that. So it's not a perfect answer, but hang in there. And we'll see what happens. And the people who should worry are the people who are not doing the homework, who are not prepped for the exams. They know that. Any other? I hope that's as good an answer as I can give you right now, Marissa. But
We'll have a sub for lab
you have a sub for lab, discussion, and lecture. I believe your lab, I don't know who your lab instructor will be, but your lecture and discussion instructor, I think I've identified that person so far. You have two? So is there a request?
Yeah.
I'll see what I can do. Okay, so where were we? Well, we will finish the chapter 17 and chapter 18 material in plenty of time for you to start and hopefully make significant progress on the homework before I go. To do that, let's pick up where we left off. We were talking about these reactions called KSP reactions. And KSP reactions were solubility product reactions in which you took something that was, in Chem 400, insoluble. In Chem 401, it is slightly soluble, and therefore it has a solubility product. KSP values are almost entirely very small, less than 1 for sure. Where were we? We had talked about qualitatively magnesium hydroxide and what happens to the pH what happens to the solubility in high pH and low pH solutions. Now we'll do the quantitative version. Quantitative, of course, means with numbers. It says assume that a buffer holds the pH at 4.00 or 10.00. What is the solubility of magnesium hydroxide at these two pHs? I will start by writing the solubility product constant reaction for magnesium hydroxide. Starts with the solid, goes to the ions. Like so. And I previously gave you, or no, I didn't. It is available on the conversion and equation sheet, the KSP value for this, which we will need to solve quantitatively. 2.06 times 10 to the minus 13. So. And I will now set up an ice table around this. Hold on. I think I'm getting carried away. I get such my natural instinct to set up an ice table that I don't need to this time, but I went to. So anyway, no ice table necessary. This is a slightly weird question because I'm telling you what the concentration of hydroxide ion is in the buffer. And that it's set, meaning that it won't change. based around these pH values. So this is a slightly weird question, and that's why we don't have to set up an ice table. When I say it won't change, that means that there's no use having a C row where it changes. Okay. So instead what I'm going to do is I'm going to write my KSP in terms of concentrations of my products. For the hydroxide, it is squared. And it is equal to that KSP value. Now at pH equals 4, and I've reminded you, a couple people of this already. I will make sure to remind everybody right now, all pHs in Chem 401 have 2 decimal places. And so on your second exam for sure, and even on your next homework, please make sure that's true. At pH equals 4, the concentration of hydroxide is 1.0 times 10 to the minus 10. And if we plug that into our concentration right there for hydroxide, and solve for our magnesium ion concentration, we get 2. Let's see, hold on. We got minus 13. We got minus 10 squared in the denominator down here. 2.1 times 10 to the 7th. Wow, that's pretty soluble. I've never seen a true molarity that big. And so our conclusion is it is completely soluble at this pH. Now we go to pH 10. Concentration of hydroxide this time is 1.0 times 10 to the minus 4. And our concentration of magnesium ion is 2.1 times 10 to the minus 5th molarity. Much smaller. And so what I started to talk about last time, about how chemists are control freaks. They like to control reactions, right? I don't care what your KSP is telling me. I'm going to change the solubility at will from infinite to 10 to the minus 5th molarity and done. And that's a large change in solubility. As based on the concentration of magnesium. Questions about that?
Where are you getting those values? Like I know you get the KSP from the conversion and equation sheet, but then where are you getting like the concentration of hydroxide and
Good question. So where am I getting my concentration of hydroxide? So I told you what the pH is.
Mm-hmm.
I can get my concentration of hydronium from this,
Right.
and then using the relationship between hydronium and hydroxide, get my hydroxide.
Okay.
So, and I skipped those steps, it's true, but that's, if you look at the POH, POH would be 10, which is 10 to the minus 10.
Okay.
Yeah.
And same thing for the
And same thing for the other ones.
Okay.
Yeah. Okay, The take-home message being that we can, so even for these sparingly soluble, not very soluble things, we can change their solubility by adding or subtracting ions, changing the pH of the solution. All right, so next example, will a precipitate form? This is Q versus KSP. Q is what's called a reaction quotient. And we've had, well, I'm going to just, Q is pretty general. Q, if you remember, just means concentrations that are not at equilibrium. But otherwise, it's the same expression as whatever your K is. And so even though we haven't used the term QSP before, QSP just means in relation to KSP. So I'm going to call it QSP. And if you remember QSP, if QSP was less than KSP, or whatever the K was, then the reaction was going to go towards products. If it was greater than KSP, it was going to go back towards reactants. And if it was QSP equaled KSP, then you were at equilibrium. All of that still applies. We're applying that same idea, though, to a new type of problem. It says if we mix a certain amount of sodium sulfate and a certain amount of barium chloride, will a precipitate form? It gives you the precipitate that is possible. We're going to write out a double replacement reaction. That's going to be between sodium sulfate and barium chloride. We know what the potential precipitate is. Because the KSP, barium sulfate, from Chem 400 last semester, we know that barium sulfate is one of the insoluble species. And then the other one is just sodium chloride. We get 2 moles of that. Not that we care, because they're spectacular. So this would be the overall reaction. The net ionic equation that we're interested in will get rid of the sodiums and the chloride ions and be left with sulfate. Plus barium ion going to barium sulfate solid. And as you were working through homework 3, I was, it's not necessary to do, but you almost entirely want to work with net ionic equations because, for example, if you work with this overall reaction, you probably have no idea what the K value is for it. But if you work with this, well, it's a KSP backwards, and you can start to see that it's a reaction that you know a K value for. And for chapter 15, 16, and 17, which we're in now, 17, to know the K value means you can probably solve the problem. Okay? So, any questions about that? Yeah, Aaron.
So we should always use the net ionic equation, or should we only try to?
So should you always use the net ionic equation? The short answer is, I think yes. Right? And that's why, as we worked on homework 3, we were getting rid of those sodium ions, those chloride ions, those iodide ions, so we could focus on the weak acid or the weak base that we can identify. So, and then there are ways to do it without, like with the sodiums in there. I just think they're more complicated. So that is my recommendation. Yeah. Although, like I would say in Chemistry 400, and is still valid now, you need to process the information and understand how to solve the problems in the way that makes sense to you, and whatever that is. So if you include the sodiums, fine with me as long as you get the right answer. Any other questions? As I said, this is a 1 over a KSP. And I'm going to treat it as such, and so I'm going to write 1 over KSP. I'm going to take 1 over 1.07 times 10 to the minus 10. And I get 9.3 times 10 to the 9th as my, well, I guess I'll call it a KC. Right? Kc is our catch-all expression for any equilibrium constant that we don't normally, that we don't know what else to call. So, and this is a Q versus a K. I guess I now should call it QC versus KC. Maybe that's more familiar. However you do it, I am going to write Kc for this reaction is going to be solid on the product side. Question?
What is the SP for KSP exactly stand for?
SP stands for solubility products. It's a good question, and if you look at, well, this is 1 over KSP. If we come over to this one, you can see that it's a product of the ions. Yeah. Does that answer your question?
Yeah.
Yeah, it's solubility product. All right, so just rewriting that there. Now I know what my QC expression is. It's going to be the same thing, but I have to figure out, based on the problem that I'm given, what are the concentrations of my sodium ions, what are the concentrations of my barium ions. Question, Hannah? What?
Just looking at it like that without plugging in any values, wouldn't it just be equal? Wouldn't KC and PC?
Wouldn't they be equal to each other? That's what we're going to do. So let's see what happens. Yeah, that's what we want to do. QC, we have no preconceived notions about what QC or what any reaction, what any Q is going to be, because we just take whatever we're given and plug them in. Now, let's talk qualitatively, or without using any numbers, without writing on the board for a minute. I'm given a concentration of sodium sulfate of 0.1 molarity. What in just this solution is my concentration of sulfate? It's 0.1 because there's one sulfate, and so you could do some stoichiometry, but I suggest that knowing this in your head is where we want to be. In just this part, the concentration of sulfate is 0.1. And if I were to ask a similar question for the concentration of sodium ions in that solution, what would that be? It'd just be 0.2. Good. Okay. I use the same concentration for the barium chloride, so the barium chloride would also be, as far as the barium ion goes, 0.1 as well. Any questions about that? All right, next. I am adding equal volumes together. When I add equal volumes, the volume doubles. When the volume doubles, what happens as a form of in the form of a fraction to the concentration of the ion? It's cut in half, right? So I'm going to write down here that instead of 0.1, it's 0.05 molarity sulfate ion. I guess and then right next to it, double the volume, halve the concentration of the ion. And if this were Chem 400, just getting there would take 5 to 10 minutes. But this is Chem 401. And I'm happy to go over this if you have any questions. Same thing for barium ion. Saves us some calculating time. Now we can plug back in and find QC. QC is going to be 1 over these two concentrations. And I get 400. And now we compare QC versus KC. QC is less than KC. That means that our reacting concentrations are higher than at equilibrium. That means the reaction goes towards products to get to equilibrium. That means since our product is a precipitate, will a precipitate form? The answer is yes. So I'll write that down here. QC less than KC. Reaction must proceed to right to get to equilibrium, forming precipitate. Reaction must proceed to right to get to equilibrium, forming precipitate. Let me write that and then I'll take Travis and Lois's questions. Travis?
So there's a QSP and the KSP. Are those ever set up in relation to greater than or equal to, like the K or QC and KC one?
Good question. So QSP versus KSP. Well, let me see if I can answer that question. So there's another whole way of doing this problem in terms of KSP and QSP, meaning that I just flip this reaction. That will flip the Q and the K as well, and you will get the same answer. Okay, so yes, there's another way of doing this, and both of them are equivalent. Does that answer your question?
A little bit, I guess just the one follow-up. Would it be the same relation as where Q is less than K, it would go to the forward reaction for the QSP and KSP?
So, if we were to use KSP and QSP, then the same relationship holds, except that since the solid would be on the reactant side, it would then tell you the reaction is going to the left to make the solid. It would still tell you you get precipitate, right? That's what I mean by saying this.
Okay, thank you.
Close.
Does QC have any
Does QC
units?
have any units? The short answer to that question is still no. And the long answer to the question is C, physical chemistry, your junior year of chemistry. No, so that's not a very good answer. Yeah, the short answer is no. The long answer is too long for chemistry 401. Yeah, I think I said that before too. Happy to talk about it in office hours actually, but it won't affect, like QCs and KCs will never have units, yet everything that goes into them will. And so your answers will have to, like, if you solve for concentrations, they have to have the concentration units. Any other questions? Marcy?
Just in case, for a 1 over KSP is equal to KC, like what is the relationship there?
So I wrote this reaction, right? And everything lately is, for whatever reaction you write, you're going to need to know what the K value is. And so since that is KSP, when I reversed my reactants and products, I put this as 1 over KSP.
And then, so I would say KSP is like kind of like a more specified version of KC.
Right. KSP is just, so KC, I could write KC for any reaction up here, right? I give you some random reaction. In fact, in chapter 15, that's what we had. We had random reactions, and we called it KC, and all KC meant was equilibrium constant in terms of concentrations. This is an equilibrium constant in terms of concentrations. We can call it KC. The only reason we call it KSP is to identify it.
I guess the question is a little less than the KC that would be like 1 over 1 over S of the
Where did I get this?
Yeah.
Oh, okay. So this is the Kc expression for this reaction. It's always products over reactants. My product is a solid, so there's a 1 in the numerator. So I guess what I'm trying to say is there's actually there's nothing like this problem, this exact problem could have been on your first exam, except I would have called everything Kcs. All of the same rules apply. And I could have said, does this reaction go, given these concentrations, does it go in the forward or reverse reaction, in reverse direction? And you could have done all of this. And what is new is just the term SP for Ks. I don't know if that answered your question a little bit. No? Maybe we can talk later and work it out, because of course we want to work it out. Any other questions? Mackenzie?
Just going back a beat or two, sorry, but what's the definition of solubility limit? What exactly is it?
Good question. What is the definition of the solubility limits? Well, good question. So solubility limit, let's say, is basically how soluble is something, right? I mean, that's saying the same thing in different words. And what we're going to see is, and I think this might be one of the examples we used. I think the example we used was actually this. And in the problem that we looked at a couple pages ago, we said there was a question mark here. For the I, there's a minus x here. And in the end, whatever is under the solid, which will always be minus x, because there will always be a 1 coefficient here, is the solubility. Sometimes we call it the solubility, sometimes we call it the solubility limit. It is how much solid will dissolve. So, and it is always the minus x. Some textbooks call it, and I wouldn't do this, call it minus s for solubility, but I prefer to use just the same terms we've always used. And hopefully it makes sense that whatever goes here is related to how much dissolves, even though the solid doesn't show up in the equilibrium constant, right? It's still related to how much is dissolved. Other questions? Cool. All right. So, take home message. Nothing new here, except we're still doing old stuff, except we're calling it KSP instead of KC, and doing that. Now let's talk about something called selective precipitation. In this end, we're going to go straight to an example. We have a mixture of seawater that contains 0.059 molar magnesium ions and 0.011 molar calcium ions. We want to precipitate one of the ions using potassium hydroxide, but not the other ion. How can we do this? That's the problem statement. Let me first start by saying that we have our KSP values. And of these two, which will be less soluble? The magnesium hydroxide will be less soluble because its KSP is smaller. Will be less soluble because its KSP value is small. So if we have these two ions in solution, which one will precipitate first? The magnesium will precipitate first because it is less soluble. So that's the first thing, is which one will precipitate first? The less soluble one. Any questions about that? Good. Here's what I'm going to do. So I'm going to punt on this question, right? And I'm going to say that the details of this question will not be on your exam. I feel like that's an okay choice to make at this point. And so, very interesting concept. I'm feeling full right now. And so I'm going to skip it, and if you have any questions about it, let me know. Not on exam. Anyway, and honestly, I'm going through this and I'm thinking that we know enough about KSPs to do fine. And any more details you can cover with me individually. Is that okay? Yeah, good. I think that's a wise choice. Yeah, because I think there are actually more interesting things to talk about, and here's what I want to say about this. One of your labs is called qualitative analysis. Qualitative analysis deals with starting with a mixture of ions in solution, adding certain reagents to them, and precipitating and separating all of those solutions. We will talk about, actually, we will probably solve that last problem in lab when we get to that lab. And any details we need to work out, like I feel like we'll talk about it enough that I feel comfortable with that. All right. Yeah, I think we'll show what we. So we'll keep going. Now let's talk about complex ions. Let's talk about what a complex ion is. It's an ion that contains a metal cation bonded to one or more small molecules or ions, such as those listed there, and many others, as we will see. We're going to talk about equilibrium constants related to this, and then we have a whole other chapter about complex ions coming up, but it's important to talk about this topic now. These small molecules or ions are called ligands. The equilibrium constant is Kf. We only know what complex ions form by what values of Kf we have. An example, we have a Kf value for this. Now, have you seen subscript F before? Delta H of formation, and so F means the same thing, formation. It is a formation constant, formation equilibrium constant. And if you remember back, we had what was called a delta HF reaction. And delta HF reactions had 1 mole of whatever was forming on the product side, and as many moles as you needed on the reactant side to make that thing. And so this one follows the same idea. The reaction, and it's here where I say any value of K goes with the reaction, just like any value of delta H1. That's going to be my product. And your reactants, and you could draw a double or a single arrow here. I'm looking at you, Kf equilibrium constant, and how large you are to say that this reaction will go to completion. And it's going to be made up of the copper 2 ion and 4 moles of ammonia. And we will talk more about this later, but just to let you know, here's the little copper 2 plus ion. Here's the ammonia molecule. According to the Lewis acid-base theory, which said that bases donate pairs of electrons, ammonia is a base. We're not surprised by that fact. It's a Lewis base. Maybe we are, and maybe we are not surprised by the fact that copper 2 ion is a Lewis acid. And we really don't spend that much time talking about Lewis acids and bases theories, but when it comes up, we like to show you what's going on. Lewis acid-base theory is huge in organic chemistry. Anyway, and so I've drawn one of them. Of course, it happens 4 times because there are 4 ammonias there. And what we will see later on is that it makes a lovely tetrahedral blue complex. But we'll save that for later. Another thing about KF values, they are generally very large. That's why we're interested in them. These are ions that form, complex ions that form completely when they do. Any questions about that? Now let's talk about formation of a complex ion and how it affects the solubility of a compound or ion. What is the solubility of silver chloride in pure water and in 0.100 molar ammonia solution? KSP for silver chloride, 1.77 times 10 to the minus 10. KF for silver amine. That's silver with two ammonias attached to it with a +1 charge. Silver we're used to with a +1. Ammonia, neutral molecule, doesn't change the charge. (1.7 times 10 to the +7, that's a large number. And first, let's do water by itself. That's what's called pure water. You'll see this a number of times, and it just means there's nothing else around. And in pure water, the only thing that happens is the KSP reaction. Now we set up an ice table around that KSP reaction. And it's not too bad of an ice table. We get that KSP equals x squared. And I'll write it a little more detailed than that. In this case, x equals 1.33 times 10 to the minus 5th molarity. That is the solubility limit. That is how much of the silver chloride dissolves. And this was the only thing going on. This was our largest K value. We're always thinking, what is our largest K value? This one. Any questions about this? All right, if there's no questions about that, then let's go on to, with the forming the complex ion. What's the first thing you notice about this one right here? Is it bigger or smaller than KSP? And it is tempting to think that we would like to deal with this first because it's our biggest K value. But in order to form any of this, we need some silver ions. So this is a case where this second reaction can only occur if the first one happens. And if that happens, that means you have to add the two reactions to come up with an overall reaction. So let me write some verbiage about that right here, and then we'll do some adding. So KF is much bigger than KSP. But needs silver ions to occur, and let me, hold on, needs silver ions from the dissolving of silver chloride to occur. So the KF reaction cannot occur unless the KSP reaction occurs. And that's a case where we will add the two reactions together to get an overall reaction. And this is a little ironic because I've seen on the homework it's been tempting to add reactions together a number of times before. This is one of the first places that we get to do it. Here's what it looks like. Write out a KSP reaction for silver chloride. Write out a KF reaction for silver amine. And the key here, by the way, is that your silver ions will have to cancel out. I have a silver ion on the reactant side in this bottom reaction. I have a silver ion in the top reaction here. Those will cancel out. Add them up, write what's left, a la Hess's law, a la a number of times before. And when we add reactions, we multiply K values. And I'm just going to go with this KC because we don't have a typical name for this. When I multiply these together, I get minus 10 and times 10, 10 to the minus 10 times 10 to the plus 7. It should be somewhere around 10 to the minus 3. When I actually do the math, I get 0.00301. And we're going to solve this in a second. We're going to see that the solubility is much larger. I wanted to take a minute out for us, though, and talk about these two reactions. These two reactions are what are called coupled reactions. Have you ever heard the term coupled reactions before? Bio 402 people. What does it mean to have coupled reactions? I don't know, but here's what I know from a chemistry standpoint. And I'm really interested in this. So this is something that I'm starting to think more about myself. This second reaction cannot occur unless the first reaction occurs. You can see that the silver is canceling out. So it doesn't end up in our overall reaction, but if you don't have silver ions for this second reaction, you can't do it. So our first picture of coupled reactions, and we do return to this, is that they have the same species in them that cancels out. One on the reactant, one on the product side. That's our first version of coupled reactions. Another part about coupled reactions is one of the reactions won't happen very easily or very much, while the other reaction happens much more easily, and you get a net reaction that is somewhere in the middle. Anyway, good. So let's solve this now. We'll continue the calculations up there. So I've run out of space, so I'm going to rewrite this reaction. I don't know if your page works to have it, but we're going to set up a nice table around that reaction. That's right here. When we do this, we start with a solid. It's still got a question mark over here. It's still got a minus x. It's still got a question mark. The problem statement says 0.100 molar ammonia. Of course, that's going to be a minus 2x. We start with the zero products. With the value 0.003, can we ignore x in this when we set up this Kc value? Probably not. Let's see, Kc. There's the expression. Do you like solving the quadratic? Do you want to solve the quadratic, or would you rather not? We don't have to solve the quadratic this time. Do you know why? Oh, well, it helps if I write the expression correctly. Perfect square. There, good, no quadratic. Square root both sides, blah, blah, blah. X equals. .00495 molar. And X is our solubility. X is our solubility limits. Okay. So 10 to the minus fifth solubility in pure water, we use get 10 to the minus 3, a factor of 100 times increase in solubility for making the complex ion. Let me see if this works. This is actually a little video. I don't know if the sound will work, but I've labeled everything very nicely here, so if the sound doesn't work, we'll still know what's happening.
When solutions of silver nitrate and sodium chloride are mixed, insoluble silver chloride precipitates from solution. When we add ammonia to the mixture, however, the precipitate redissolves.
That's it, believe it or not. That's it's amazing to me. So Any questions about this problem?
Wins.
Keep going. All right.
Win-
Good. All right, let me erase. We got one more thing to talk about. Finally, amphoteric metal hydroxides. Many metal hydroxides are insoluble. ... In pure water. If we look at impure water here, we have KSP of 1.3 times 10 to the minus 33. Pretty darn insoluble, yes? Yes. All right. And if you were to set this up and solve for the solubility, you get an expression like this, right, where the 3 shows up as a cubed. There'd be a 3x in here, right? This is shortcut for a KSP solubility table. Anyway, I want to show you the result for solubility. And you would solve and get 2.6 times 10 to the minus 9th molarity. As the solubility. So not very soluble. All metal hydroxides become more soluble in acidic solution, shifting the equilibrium to the right by removing hydroxide. Well, if I write out the KSP reaction now, and I tell you that we are adding acid, when you add acid, you're adding hydronium. Hydronium reacts with hydroxide to remove it. Since there's less hydroxide around, which way does the reaction shift to reestablish equilibrium? It shifts to the right. When you shift to the right, you increase solubility. Now, we talked about that before, but it's worth doing again. Add hydronium. Hydronium reacts with hydroxide to decrease hydroxide concentration. Shifting the reaction to the right and increasing the solubility. And we won't use any numbers for that one. I think we're going to use some numbers down here. Questions about B? Now let's move on to C. Some metal hydroxides also act as acids, becoming more soluble in basic solution. Here's a KF. We have a KSP. We're going to do a very similar thing to what we just did before. In order for the aluminum hydroxide ion to form, some of the aluminum hydroxide must dissolve. Therefore, this one's much bigger. We have to write the two reactions, add them up, and then come up with an overall reaction. We're going to do it again, except now for aluminum hydroxide. my KF is a formation. I write it as a product. I take what I need on the reactant side. The question?
Yeah, I'm sorry. Where did you get that extra? You have 3 on the first that you wrote out for the KSP reaction. You have the 3 hydroxide, and then on the 4.
Good question. Where did I get 3 and 4? Well, I see 3 here, and I see 4 here. So I have no preconceived notion about how many hydroxides there should be, except that the problem told me. You know what I mean? Like this one must contain 3 hydroxides. You're right. So if where you're going with this is the hydroxides don't totally cancel out, you're right. And that's okay. I mentioned before that silver canceled out in the previous example, and aluminum will exactly cancel this time.
You're given, sorry, AlOH3.
Given aluminum hydroxide.
I'm sorry, I didn't know those were related. Okay.
Yeah. And incidentally, this is the second example in a row that I've done of coupled reactions. Hint. Well, I skipped that other thing entirely. Anyway, take it for what it's worth. So, but to get more specific, and I'll take your question, David. To get more specific, Hannah. So the only way we know how to do any of these KSPs and any of these KFs is if you're given them. And the worst case scenario is you have to go to the conversions and equation sheet to find them. Right? But other than that, again, this is Chemistry 401. We don't know a lot of reactions to write. We know Kas, Kbs, Kw. Now we're adding in KSPs and KFs. And other than that, I have to give you the reaction with the Kc and tell you. So I don't know if that helps, but
Yeah, I guess I'm just confused because it says like example aluminum hydroxide on under C where we are,
Mhm.
and it's for. But I guess like what information would be given to us for us to know to start with the aluminum hydroxide?
That's a great question. So maybe another way of phrasing your question would be, if we were to get this question on the exam, what would it look like? Or on your, I don't know what it looks like on your homework. You have the homework this time. But if this question were to appear on your exam, it would look like this. Calculate the solubility of aluminum hydroxide in pure water and in some concentration and in some concentration of hydroxide. And then it would have to tell you that aluminum hydroxide forms a complex ion. And tell you what it is. If not, say, go to the complex ion list and find it. Yeah, no, and that's a very good point, by the way, because I was just noticing that in this particular problem, I would have to tell you that the concentration of hydroxide initially is 0.10 mole. So fair enough. Let me see. I think I brought a copy of homework 4. I lost it though. I was going to say, because how I wrote it on your homework is probably how it's going to show up on your exam. You have homework 4? These are like little Bibles to what can be on the exam. Oh, page 9. Oh, did you look at homework 4 yet? Probably not. I know. Homework 3 was just due. I've instituted these things called roadmaps because I want to give you a little bit more hints, especially for the harder problems, on what the path is. Let me see. Oh. I'm glad we did this. Do you see page 8, number 8? Skip it, because that's the thing we skipped in lecture. It's a great question. I have the answer key. Happy to talk about it. But it says we want to precipitate one ion but not the other. There you see. All right, number 9. Silver is often mined as silver sulfide, a highly insoluble compound, then is mixed with sodium cyanide to increase its solubility because silver ion and cyanide ion form a complex ion. All right, sounds like this kind of thing. Calculate the solubility of silver sulfide in pure water and in 0.100 molar sodium cyanide. Then calculate the factor by which the solubility has increased by calculating something very specific that I've written out for you. That is how it will appear. So, and it's true, you still have to look up what are the complex ions and what is the KSP value. But based on that problem statement, you should know to do that. Does that sound fair?
Yeah.
Or like it may be fair in 3 weeks when you get similar questions on the exam. I know, it doesn't seem fair yet, but it's a process. Anyway, but that's part of this, and I worked very hard on this one actually to have it be like this. So, and I will work even harder to make your exam clear as well. And that's only because I appreciate all the hard work you're doing, and you should have success for your hard work. Anyway, yeah, no, so that's happy to talk about all these things. Any other questions? David, yes, you had a question for me back. Thank you.
So in the last problem and this problem, the first equation can move forward or backwards, but the second reaction in the last one and this one only moves forwards. Is that because we're only looking for the forward reaction? Does it have the capability of going back and forth?
Good question. You've noticed that this is an equilibrium arrow and this is a goes to product arrow. And a couple things I'll say about that. First off, I don't care what kind of arrows you draw. Like the default is to draw double arrows everywhere because on some level every reaction is an equilibrium reaction. I've chosen to draw this as a single arrow because it goes to products so hard, right? But if I drew an equilibrium arrow here, it's true, this reaction is an equilibrium. It's just that there's so little reactants left. So I don't know if that addresses your question, but you can draw them always like this. I tend to draw for smaller values of K, the equilibrium arrows, and for larger values of K. Although, so interesting to think what's going to happen to the arrows in chapter 18. Anyways, stay tuned. But yeah, but now I'm going to get, in that one, it's going to be 10 to the minus 33 times 10 to the plus 33, so it's going to be very close to 1. I'm going to put my double equilibrium area back in, because that reaction doesn't go to completion. Any other questions? If not, we have a few minutes left. I love this idea of coupled reactions though, and just to give you an idea, this is me evolving as an instructor and creating more headaches for you. But hopefully, no, like I'm really interested because I don't understand, like on the homework, the extra sheets that are going to replace some of your lecture sheets, they deal with glycolysis and coupled reactions of glycolysis. And now now I'm seeing it in other places as well. I'm thinking about what it means to be a coupled reaction. Anyway, it means you need aluminum ion for both of these, and so one reaction drives another reaction to occur, and we will talk about what that means in terms of thermodynamics for next year as well. Anyway, in the end, just write what's left. Ooh. Cross out 3 of those as well. We'll just call this a KC because we don't know what else to call it. Except it's in terms of concentrations. And I get 3.9. And you could set up an ice table around this. There's an ion here, there's an ion there. I'm going to try and finish chapter 17 today. And so I'm going to go on to this last slide. But there's an ice table to do here, and it's similar to the last one. Last topic, small metal cations can have acidic properties and have a Ka value. Aluminum is an example of that. If you look in your conversions and equation sheets, you will find this value and several others. When you do, you will actually see this species. This is another complex ion. And so from that standpoint, it's new. But from every other standpoint, it's exactly the same. Meaning, if you have a Ka value, you write whatever it is plus water, goes to hydronium plus conjugate base. Is this a weak acid? It is a weak acid. Oop. Since it's an acid, take one of the H's, have it go along the proton rainbow. And now there's one less H over here. So technically the way to write this is aluminum with 5 waters and an OH. That'll have a minus charge as well. But otherwise, this is exactly the same as every other ice table. And lo and behold, that is the end of lecture. That is the end of my time. I'm happy to take any questions, but that's it. Dylan, question? Oh, why is it minus? Thank you. It should be 2 plus. Thank you. I wanted to write, so it should be 1 less. I forgot there was a 3 plus there. Thank you, Dylan. Travis, thank you. Now we're done. And we'll pick up